I recently completed a quantum mechanics course. In it, there were difficult questions that I don't know how to do to this day, easy questions which I sailed through with relative ease, interesting questions that really made me understand the physics behind it all, and the stuff I actually signed up for. The rest of this video will be my thoughts and comments as a philosophy student, not as a physics student, because that's the department I am based in. And with that, let's begin. In week 2, we began with special relativity and Einstein's two postulates, the fact that all physical laws hold regardless of which frame you're in, and the speed of light being the same no matter what. The first one is more easy to accept because, well, it's highly logical, it's built on logic. Okay, fine. But light, why is it the same speed? What's so special about it? What I was really trying to ask, naively, intuitively, is what is matter? What is the nature of light? And that's actually where we began in this course with the Michelson-Morley experiment. We actually disproved the ether very, very early on and introduced the atomic model theory within special relativity. We use electrons and beta particles to going very near the speed of light and just did questions about that, for example. And of course, that set us up for nuclear physics, which used the same concepts and introduced radiation, as we saw just now. Very, very nice indeed, which flowed very nicely into, well, old quantum mechanics, specifically the quantization of light. What we saw was the photoelectric effect, how it was not explainable within classical mechanics, how we needed old quantum mechanics to, explain what is happening when light does something to metal. Of course, this allowed us to explain the double slit experiment, how light is actually a particle and a wave at the same time. Fine. That's hard to accept, but it is acceptable. The consequences are perhaps more uncomfortable because it stood out to me because it was uncomfortable with its implications, but also because it contained very nice mathematics, which allowed me to accept that old quantum is true. For example, you can just use these two equations on screen and it works. It works because it is mathematics which agrees with the experimental results. So I cannot dispute it because the maths and physics just say it is. Fine. The weird consequence is, what does it mean for something to have a matter wave? And why does it disappear when I don't move? More specifically or more generally, what does it even mean for something to be a particle? What does it mean for it to be a wave? How or why can something be both a particle and a wave at the same time? How can we assign meaning to that? Now, my professor, sometime in week 7, because this is where we are at, mooted or suggested the reconciliation of this via models, that each of these things, particle, waves, duality, they are all models in helping us understand how the world works. So when we have something newer, better, something that throws everything into chaos and out of the window, we can just update our thinking, take the new model as it is, and see what works and what doesn't work from there. Of course, a better model would work with pre-existing concepts and explain more than what is already known. That's a topic for another day. But of course, thinking about these things as models did not make me any less uncomfortable with the concepts. I still had difficulty accepting everything as true. I mean, I accepted it as true from a mathematics point of view, but not as a physics point of view, because maybe I'm just not a seasoned physicist, that's why I'm having a lot of trouble accepting any of this. But yes, the tension is there. Until it escalated my tension all the way to new quantum, or, where we are today. Specifically, or summarily, in the Heisenberg uncertainty principle and the wave equation. I'll focus on the first because, yes, we cannot measure momentum and location, position accurately, precisely. There is an uncertainty to one or the other, depending on how you measure it. Basically, if you measure momentum, precisely, you cannot measure position precisely. The lower bound between these two is h bar over 2. Same thing can be said for time and energy. Why h bar over 2? Why position and momentum? Why not time and momentum? Why not energy and some other combination? Why these combinations and why h bar over 2? Why is the limit as it is? Just why? I was told that the uncertainty principle was constructed based on the non-commutability of the operators. That is, if you find a non-commutable pair of operators, there will be an uncertainty attached to those two things. To that pair specifically. Okay, fine. This was a case where the model way of thinking and remembering that maths should be secondary helps to resolve this tension and uncomfortableness. But that does not help fully with wave equations for several reasons. While the operators are still there, I still don't know why the position operator is x, why the momentum operator is negative I h bar del psi del x. Just why? And why are you allowed to square them both inside and outside the bracket notations? Of course, I'm looking at this from a mathematics standpoint because that's what I'm most comfortable with. However, I can resolve this tension at least to my best ability by remembering that the mathematics is a consequence or the result of our experimental values and results. That all of this happened because we looked at the universe and said, so this is what it's like. But that kind of line of thinking can only take you so far, and I'll show that with the Schrödinger equation. We see the general one, IH bar del whatever, becoming a Hamiltonian in respect to psi. 1DST, same thing, there's a Hamiltonian hidden right there. Although the potential operator is uncomfortable, it is an operator nonetheless, and we've already had position and momentum, we might as well have potential and all the rest, fine. And then the time-independent TISE, you can very clearly see the relation between the Hamiltonian in the general equation and the energy eigenstate in the TISE. So what does it even mean for a Hamiltonian to be a stationary energy eigenstate? Because eigenstates and values are numbers, right? I mean, I guess energy can be number, but I guess I was looking for a deeper meaning that, is usually waved away in other physics courses because we are doing quantum after all. Maybe I'm just confused about linear algebra and everyone's just accepted that mathematics perfectly describes physics and we can perfectly assign physical meaning to mathematical concepts. Fine. If you accept that, that still does not answer the question on why the wave equation collapses upon measurements, or why all measurements are eigenstates and values. These are the mysterious rules of the universe that no one has answers to, and I'm not entirely sure whether I can say with confidence that the wave equation collapses upon a measurement. I know it's the canon, the standard interpretation right now, but is it really? I haven't read enough philosophy of quantum mechanics, but I feel uncomfortable. Like, I've been trained enough in philosophy and everywhere else that I can say that there is some contention or tension beneath this statement that the wave equation collapses upon a measurement. I'm leaving out some intricacies which might shed more light on this situation. And right now, I'm just sitting here saying this is fine, but is it really? I want answers, and this course has done well for me. I've learned a lot, but at the same time, I finally see where the philosophy comes out, and I'm just waiting for answers.